In the last section, the last supplement, I said that the square root of a number squared was just the number. And that's because squaring and unsquaring a number are the same operation in reverse. Squaring a number does something to that number, and unsquaring it does the opposite, undoes the squaring. It was the same thing with the cube root of a number cubed. If I cube and then uncube a number, or in fact, if I uncube a number first and then cube the result, I still get that same number back. I also said that what this is called is inverse operations. Operations doing something to a number that undo each other are called inverse operations. The thing is, squaring and unsquaring, cubing and uncubing are not the only inverse operations. Since subtraction undoes addition, addition and subtraction are inverse operations. What undoes multiplication? Division. So multiplication and division are inverse operations. Any two operations that have the opposite effect, that undo each other, are inverse operations. We can use this undoing property to solve equations. Here are some very simple equations that you already know how to solve. And in fact, you already know that what you need to do is the inverse of adding 2. It's just that we haven't called it that before. The inverse of addition of 2 is subtraction of 2. So here we're using the inverse operation to addition to solve our equation. Subtraction is the inverse of addition. The inverse of subtraction is addition. So here we choose to add 2 to both sides. The reason this works is that we're subtracting 2 and adding 2. We're doing this, minus 2, and then undoing it, plus 2. So that leaves me with x minus 2 plus 2, or just x. And on the right-hand side, of course, I have 5. To solve this equation, I have to look at the operation that's being performed here. Although there's no operation symbol, it's understood that it's times. The inverse of multiplication by 2 is division by 2. Multiplying and dividing by 2 leaves me with just the x. I've taken x, multiplied it by 2, turned right around, and divided it by 2. The inverse of division by 2 is multiplication by 2. Dividing x by 2 and turning right around and multiplying it by 2 just returns x. So there's an example of 4 basic equations, each one with one of the basic operations: addition, subtraction, multiplication, and division, solved by using the inverse of the operation in the problem. Remember that the square root of a number squared is equal to the number, and also that the square root of a number, all squared, was equal to that number. If I'm given the equation, the square root of x equals 4, I don't want to know the value of the square root of x. I want to know the value of x. What can I do to this to make it look like one of these so that I can get x out? I think the easiest way would be to square this expression. But if I do that, I must do it to both sides. The square root of x, all squared, is just x. That's this property here. But 4 squared is 16. So the shorthand here is that you can square both sides of an equation. Does this solution make sense? Here's what I started with. The square root of x equals 4. The square root of a number is the number I have to square to get the number. What number do I have to square to get x? Well, according to this equation, that's 4. 4 is the answer. So 4 is the number I have to square to get x. So what happens when I square 4? I get 16. So this answer does make sense. I got it by squaring both sides of the equation. And I chose to square both sides because I knew that that would undo this square root. It's the inverse of the square root. This problem is very similar, but it's a little bit different. What if I start with x squared equals 16? Well, this is a very simple equation, and I know the answer is 4. But let's just take a look at how to approach a problem like this so that we can answer the more complex problems later. Remembering that I can do anything I want to both sides of an equation as long as I do it to both sides, and remembering that what I'm trying to do is get into the x here so that it's completely by itself. It seems to me that the easiest way to get the x by itself would be to take the inverse of squaring it and make it look like this. In other words, take the square root of the left-hand side. Now I'm going to have just x. But since I've taken the square root of the left-hand side, I must also take the square root of the right-hand side. And the square root of 16 is 4. But in this case, there's a little bit more to it. Here's what I started with. X squared equals 16. That says that some number squared is going to give me 16. It's true that the number x is 4 will give me 16 when I square it. But it's also true that the number -4, when I square it, will give me 16. So how do I know which one it is? Actually, I don't. In an equation like this, when I choose to take the square root of both sides of the equation, I should indicate that I don't know whether it's the positive or negative square root of 16, the positive or negative 4, which, when I square it, will give me 16. In other words, x could either be positive 4 or negative 4. If I square positive 4, I'll get 16. If I square negative 4, I'll still get 16. This equation has two solutions. I would read this, x equals plus or minus 4. You could say x equals positive or negative 4, but that's a bit of a mouthful, and most people just say plus or minus. Why didn't I have to worry about that over here? Well, in this case, I squared both sides of my equation. If x is a negative number, and you take its square root and then square it, you're going to get a positive answer, simply because you squared it. Anytime you square a number, you end up with a positive answer. Positive 3 times positive 3 equals positive 9, and negative 3 times negative 3 equals positive 9. This is 3 squared. This is negative 3 squared. I've squared a negative number and ended up with a positive answer. So in this case, because I'm squaring both sides of my equation, I know my answer has to be positive. On this side, I chose to take the square root to make my left-hand side look like this. I knew that if I did that, I would get just what was inside, in this case, the x. Because I did it to the left-hand side, I also had to do it to the right-hand side, but that was my choice. Earlier on, I said, if I want the positive answer, I'll give you the positive question. If I want the negative answer, I'll give you the negative question. But these come with the square root already included. This one didn't. Remember, I started this equation like this, and I chose to take the square root of both sides. That was my choice. If I do that, then I have to consider that it might have been the positive or the negative 4, which gave me the value of 16 when I squared it. If x is equal to positive 4 or x is equal to negative 4, then x, when I square it, is going to give me positive 16. Here's the same equation twice. 3 times x minus 2 equals 12. We've solved equations like this before using distribution. Let's do that on this side. 3 times x gives me 3x, minus 3 times 2 gives me 6, and that's all equal to 12. Now, add 6 to both sides, and I have 3x equals 18. Finally, divide both sides by 3, and I get x equals 6. I can write this with or without deleting 1. You can also do this problem using inverse operations. Notice that the parentheses x minus 2 could be thought of as sort of a box. I'm multiplying x minus 2 by 3. So I can undo that multiplication by dividing both sides by 3. Undo this multiplication. X minus 2 times 3 divided by 3 is just x minus 2. On this side, I get 12 divided by 3 is 4. The inverse of multiplication is division. Now that I have x minus 2, a much simpler expression on the left-hand side, I can just add 2 to both sides. This gives me x equals 6. In fact, I get the same answer, no matter how I do it. But notice how few steps this took. Division, addition. Here I had to distribute, then add, then divide. The more complex the equation is to start with, the more steps you'll have to do. But using inverse operations, oftentimes the number of steps you have to take is reduced. Here's the same problem again, but what if it said 3 times x minus 2 all squared? In other words, this whole thing, x minus 2, is squared. I can still solve this using inverse operations. If I pretend this is in a box, and look at the fact that the box squared is being multiplied by 3, the inverse operation I need to do first is division. This whole thing times 3 divided by 3 is just this whole thing. This whole thing, this time though, is not just x minus 2, but x minus 2 squared. Continuing using inverse operations, I notice that my box is squared. So to undo this squaring, I can unsquare both sides. Unsquaring both sides. This whole thing is being squared and unsquared. So I need to ask, what is it that I have squared and unsquared? What I have squared and then unsquared is x minus 2. That piece there. Remember in earlier simple examples, I said that since I didn't know whether it was the positive 4 or the negative 4 that when I squared it would give me 16, I had to consider both the positive and the negative 4. Whenever I take the square root of both sides of an equation, write plus or minus in front of the square root on the right-hand side. So that means that I need to write a plus or minus here. I'll bring down my equals, I'll bring down my plus or minus, and I'll bring down my square root of 4, but I can evaluate it. What is the square root of 4? It's 2. I don't really need these parentheses. I had them here because I wanted to indicate that it wasn't just the 2 that was being squared, and it wasn't just the x, it was the whole thing. I needed to say everything in here was squared, everything in the parentheses. Now that it's no longer being squared or unsquared, I don't need the parentheses. I can continue to solve this problem as before. Add 2 to both sides. When I do, I get not just 2 plus 2, but plus or minus 2 plus 2. Positive 2 plus 2 is 4. Negative 2 plus 2 is 0. So this equation actually has 2 solutions, 0 or 4. This is my answer to the original equation. A note about notation. Instead of writing plus or minus 2 first and then adding 2, in later problems, we'll see these written with this number first and then the plus or minus number. For that reason, I'm going to start writing these so that I write this number first and then the number up here. It may feel a little backwards at first, but you'll get used to it. What I end up with when I do this is 2 plus or minus 2. In other words, 2 plus 2 or 2 minus 2. 2 plus 2 is 4. 2 minus 2 is 0. I get the same 2 answers as I did this way. They may come in a different order, or you may just choose to write them in a different order. The answers are still 0 and 4. Here's another example of a problem that's squared. So to solve it, I need to unsquare it. Unsquaring both sides gives me this. Remember to take plus or minus on the right-hand side. The fact that I've squared and unsquared the left-hand side means that I can rewrite it with just the stuff that was inside the square root. This is now equal to plus or minus. Evaluating the square root of 3, well, I can't. 3 is not a perfect square. It can't be simplified, so I just need to leave this like this. Now I can continue solving as I did earlier in the quarter. Add 5 to both sides. 2x equals, and here I'm going to do what I promised earlier. I'm going to write the 5 first, and then plus or minus the other number. Finally, I still don't have x completely by itself yet. I need to divide both sides by 2 to isolate x completely. My answer here is 5 plus or minus the square root of 3 all over 2. There is nothing else I can do with that. That's my final answer. You can find a decimal approximation for this number, or for both of these numbers. There are actually 2 answers here. If I knew what the square root of 3 was, I could add it to 5 and divide it by 2, and that would give me one of my answers. And if I knew what the square root of 3 was, I could subtract it from 5 and divide that by 2, and that would give me the other answer. So although I only have one expression here, the plus or minus tells me I have 2 solutions. With this equation, the x is kind of buried here inside this big expression, and this whole expression is inside a square root. So to get at x, I have to attack it from the outside, and the first thing I need to do is get rid of the square root symbol. So what I'd like to do is square both sides so that the squaring and unsquaring will cancel each other out. But square both sides. Whatever I do to one side, I have to do to the other. On the left, I now just have 2x minus 5, because that's the thing that I unsquared and squared, or squared and unsquared. The 2x minus 5 is the thing I was operating on. On the right-hand side, I just have 9. I don't have to worry about plus or minus here because I'm squaring. Squaring any real number gives me a positive number. Now I can proceed as I might have done in a previous chapter. This problem only has one solution because there was no plus or minus anywhere in all of my work. Here are a couple more examples. One where I'm going to have to unsquare to get in to x, and one where I'm going to have to square to get in to x. We'll start with this one. I can't just unsquare this piece. I have to unsquare both sides. And I could do that. I could unsquare both sides now. But if I did that, I'd have a square root of 2 inside my square root. And that's going to be really hard to deal with. So let's start by remembering that I can take this whole piece and think of it as being multiplied by 2 and use the inverse of this multiplication by 2 to undo this, which leaves me with x minus 3 squared. I've undone the times 2. Now I can undo the squared. If I choose to take the square root of both sides of an equation, I want plus or minus the square root of the right-hand side. Squaring and unsquaring leave me with just the thing inside. The right-hand side is plus or minus the square root of 50. I can add 3 to both sides, but before I do that, let's take a look at how else I can write the square root of 50. 50 can be thought of as 5 times 10, and 10, of course, is 5 times 2. So I can write 50 as 2 times 5 times 5. What that means is that the square root of 50 can be thought of as the square root of 2 times 5 times 5. I've just changed the way the thing inside looks. But now, observe that I have a pair of 5s on the inside of the square root, so I can bring that out. Then I have times the square root of 2, because 2 doesn't have a pair or a partner. I need 2 copies of 2 to bring one out, and I don't have 2 copies, so it gets stuck, left behind inside. I can write the square root of 50 as 5 square roots of 2. So I can write this equation as plus or minus 5 square roots of 2. Now let's add 3 to both sides. X equals, remember I said I would write this number first? 3 plus or minus 5 square roots of 2. This is my answer. If I knew what the square root of 2 was, I could multiply it by 5 and then add that to 3. 3 plus that. If I knew what the square root of 2 was, I could multiply it by 5 and subtract it from 3. 3 plus whatever this is and 3 minus whatever this is are my 2 answers. But I don't know what this is, not exactly, unless I leave it like this. So this is my final answer. On this side, I had a squared, so I unsquared. I chose to take the square root of both sides. On this side, I have a square root. So to undo this, I need both sides. This whole thing here is multiplied by 3. So to undo that multiplication, I'm going to divide both sides by 3. In other words, this stuff is multiplied and now divided by 3, which leaves me with just this stuff, the stuff that was multiplied by 3. 48 divided by 3 is 16. Now I have just a square root on the left-hand side. So now I can choose to square both sides. Unsquaring and squaring leaves me with the stuff that I did that to. X plus 5 is what I took the square root of. That's what I chose to square. Squaring and unsquaring x plus 5 gives me x plus 5. 16 squared is 256. And then solve. The bad news is this video has been a bit longer than most of them. The good news is that this is the only video for this whole section. I hope you'll recognize that most of what we've done in this section is more or less intuitive. Whatever you do to one side of an equation, you have to do to the other side. And however a number is attached to the variable, it can be unattached by using the inverse operation. Using inverse operations, we work our way in from the outside. Here we divided, then unsquared, and then added. Don't forget, when you take the square root of a number, take plus or minus the square root, because you don't know which number, when you squared it, gave you 50, the positive or the negative. You only have to do that when you choose to take the square root of both sides, not when you square both sides, because when you square any number, positive or negative, you get a positive answer.